I didn't set up very many PowerPoint slides, hardly any at all. So what I'm interested in, and what the Facebook message said, was come here with your telescope problems. So I'm going to set it up into a few different areas, and they're going to be setup, collimation, cleaning. I think that's it actually. Setup, collimation, and cleaning. If there's anything we haven't covered, then feel free to ask away. I can't promise to know the answer to all your questions, but we have got a few people around who may be able to help with the whole range of questions. So don't feel constrained to what your problems are. This is a clinic, so we're going to help each other as well. So I'm certainly going to have a good go at answering your questions first, but actually I know there's a lot of people around here who know more than I do. So if we can get together and have a good kind of collaborative session, that's really what I want to do tonight, if that sounds good. So I'm going to start off with telescope setup. So I think for me, when I first started in astronomy, and you first get a telescope and you take it out of the box and you're all excited about it and you don't really know where to go, I got the telescope, threw it outside on the back deck, I looked at a few things and realized I didn't really know how to work this damn thing, and then I tried to start understanding it. And for me, I think probably the hardest thing to get my head around in those first sort of few months was how the sky moves, getting an understanding why do you have an equatorial mountain, really how does that work, and how do I point it in the right direction. I kind of vaguely knew where south was, but then was surprised that south wasn't anywhere near where south was on my compass. So that kind of setup can be quite daunting for a new telescope user. Even where you don't need to do any alignment, so you've got something like a Dobsonian here, which literally you do, take outside, plonk it down, and look through it. Actually understanding, you know, where do I look? How do I set up the finder? How do I make sure I'm pointing in the right place? It's really kind of hard to tell what I'm looking through the finder, and how does that relate to what's through the main scope, that kind of thing. So these setup things, these early things, I know we've got a few kind of beginners in the audience as well who are just getting into it. So over to you guys. Give me some questions. Give me some, what challenges have you had, or what things have you overcome? This is upside down, so the questions are at the beginning, not at the end. So who's going to warm us up with a question first?
Hey, hello. How do you avoid moisture? And we might take it out with it.
So avoiding moisture, so in Auckland, that's you're going to get that. There's just no question. We have a very humid atmosphere. And the moisture in general on the outside of the telescope isn't going to cause you any problem. What you get problems is if you've got a Schmidt-Cassegrain or a refractor getting moisture on that front glass surface. Sometimes on a Newtonian, you'll get dew on the secondary mirror. So there are a number of ways to do that. The simplest kind of way to attack that, which is kind of the low-tech way, but actually it's a really effective way and is better than some other methods, some other higher-tech methods, is to use a dew shield. So really you can use anything for this. I kind of like to use that sort of thin, medium, or high-density foam used for like yoga mats and things. You can get it from Para Rubber and places like that. Get a length of it that's the size of your telescope, wrap it around. Now you can either just tape it there, you can just use a bit of cardboard, to be honest, and come out a ways in front of your telescope. Now, it doesn't have to flare out or anything, it can just be parallel, because remember the light that's coming into your telescope is all parallel. So any tube that just comes out, and make it so that if you were looking at it from above, where you're normally kind of viewing, that imagine it's raining straight down, you're not going to touch that surface. So come out a decent size. So the bigger your telescope aperture, the longer you need to have your dew shield. So that's really simple, but it's really effective. And this is why Newtonians in general don't really suffer from dewing, because your mirror's all the way down here. This whole telescope's a dew shield. Now, if you buy a refractor or something like that, then it probably have a little slide-out built-in dew shield. Sometimes they're not really long enough to do the job. Now, the other way of doing it, which is a little bit more high-tech, I guess, or what you might want to do if you're doing using an SLR camera, where you've got that on a tripod, you're tracking that, is to heat the end of your telescope lens or your camera lens. So you can buy juice straps, so they run off 12 volts, and they heat. They put a not to hot, just to a little bit above ambient. And they're a strap that will go around the end of your telescope, used a lot on SCTs as well, Schmidt-Cassegrains. Plug them into your power, and it just keeps the front of the telescope slightly warmer than ambient. Now, another way that Jonathan's around somewhere, and another way that he will do it on his camera is, Jonathan's there taking photos with his camera, is to use these chemical handle warmers that you can get. So, so the ones where you kind of break them or you rub them, or you can get, they're not quite as good, but the reusable ones where you click a button. Now you can wrap a couple of those around the end of your camera lens, and that'll just keep that slightly above ambient. Now you don't want it too hot, because then the sort of thermal currents from the heater is actually going to cause you just as big a problem. So, so that's a great question about doing.
Just one thing, if you want to get those, Chemist Warehouse have them at a really good price, the ones that are like a powdered one that you shake up, and they last for several hours.
Oh yeah, I mean, Jonathan's disappeared, but I know that Jonathan's done whole night's worth. And how long do your hand warmers normally last on your lens?
About 7 hours.
Yeah. So it's a cheap way of doing it, and easy. You don't need to have a power source.
I use them on my finder scope.
Yep.
And the way I attached them was quite cheap. Go to the dollar shop and get those wrists.
Oh yeah, the furry kind of headbands.
Yep.
Tennis and that. Yep.
And you can just slide that over the top and it holds it in place. And
yeah, I think that's what Jonathan does actually. Something like a wristband or something like that.
Yeah.
Yeah.
Velcro straps work as
Velcro
well,
straps. Yeah.
the ones you can cut off. And, yeah.
Neville, you had something?
I want to know how do you stop the finder scope from going out?
So same. So you can use exactly the same thing. So you can create yourself a dew shield or these hand warmers again. You can just wrap one of those. As we were just saying earlier, you could use like a wristband like you get for tennis. Hold one on the end of there. Just keeping this front lens a little bit warmer than the atmosphere around it, and you'll find that actually works really well.
Did you do the same on eyepieces?
Sorry?
Did you do the same on eyepieces?
I don't know. I've never tried it on an eyepiece.
When
It's,
it gets really bad, eyepieces do fog up.
yeah, they do fog up. Eyepieces are a little bit more resilient to you cleaning them and wiping them as long as you do it gently. So the coatings on an eyepiece are not necessarily quite as fragile as the coatings on other surfaces. And your biggest problem actually with an eyepiece, as we'll talk about with cleaning, is actually oil from your eyelashes. So you get that along with dew and it kind of exacerbates it. I guess it would work. I've never tried it. So maybe your next outreach you could try it and see how it works. At least it'd be nice and warm when you're looking through the eyepiece.
If you're stuck too for your finder scope, just a piece of A4 paper works really well.
Yeah. Yeah, absolutely. So at a pinch, if it's dewing up and you can't do anything and you haven't got anything at all, go get a newspaper, a magazine, or a bit of cardboard, rip up an old cardboard box and get some tape or some string and just create yourself a dew shield that's coming out. You will be surprised how well that works. It's actually, you don't need any of the technology to solve that. So anything else in setup? So who's had challenges in getting the telescope set up and understanding it?
Yeah, it's about a mount. So I've got the Altaz Pro mount. And it's a leveling issue.
Yep.
So I set the tripod of the mount up, level it, then tighten it up, level it, and try fixing the leveling again. But then when I put the telescope on, it usually keeps the level all right, but when the mount starts to spin, the leveling just goes completely off.
So is the tripod moving? Is it stable? Is it? So that tripod's definitely not moving. So how do you know the leveling's changing? Is it just based on the level that's
based on the bubble?
On the bubble level. So the bubble levels are generally a bit of a guide. Now what I would normally do with those bubble levels is set up, note the position of the bubble, and then move the mount around and have a look. If the bubble level is right, and it's leveled, as you move it around, that bubble won't change. Sometimes with those bubble levels is the way that they're mounted and the fact that they are, because they're generally made of plastic or glass, they're mounted in some kind of cement, and then they're in an aluminium housing. What can happen over time is that it contracts and expands at different rates, and sometimes they're not quite as level as they start off maybe at the factory when they're tested. So another thing that's useful that you can do is if you've, you can get like one of the little, I normally in my box, I've got a little one of those plastic levels that you might clip to a piece of string. So, you know, like if you're building a wall, you'll get a piece of string or plumb line and you'll clip a little level to it. One of those is a really useful little level if you're leveling anything, and you can just hold that up against something that's horizontal and see how that reflects with the bubble level. And obviously you can turn it around and that's going to get you different axes. So 90 degrees is going to tell you whether that's giving you the right answer or not. So what I found sometimes is those bubble levels are not as, you know, completely accurate as you might want them to be. So you might find that it isn't quite level when you started off. So it's not moving, it's just that you didn't start off perfectly level. Does that make sense?
Or if it is a tripod, maybe it needs to be a sturdier tripod for that.
Yeah, well, if it's a tripod that came with it, it will be suitable for the job.
Oh, and what sort of ground have you got the tripod on?
Well, it's mostly what I've used has been concrete.
Yeah.
Yeah.
So it is. So leveling is an interesting one actually. So on an Altaz mount, you need to level it so that the computer in the Altaz mount knows when it's moving with respect to the horizon. On an equatorial mount, you'll find kind of two camps of people, and most people will say you start off and level your mount, make sure it's all level before you start, and then do a polar align. And you get other people who say, nah, that's rubbish. You don't need to level your mount to polar align it because leveling has nothing to do with it. If your polar axis is pointing at the point in the sky where the north or south pole is, then you don't need to level it. And kind of both of those arguments are true. My advice is if you're using an equatorial mount, then definitely level it. And I'll carry a level around for the same if I'm setting up a portable one, make sure that it's level, particularly in kind of the north-south axis. And the reason that you want to do that is if you're going to refine your polar alignment, then whatever tools you're using, even if you're using a camera, which is going to tell you move up, down, left, right, or if you're doing something like drift alignment, then your adjustments, so the way you do polar alignments is you refine it, moving it left, right, and up, down to get the center of your scope pointing at the south celestial pole. If you're not leveled, whilst you can make those adjustments, it'll be harder because every time you move left, for example, in this case, you're moving down. Every time you move up, you're moving right. So that's an exaggerated example if you don't get it level. So yes, you should always level mounts. It makes your life a lot easier. Setup. Any other questions? So I'm really making you guys drive this. It's normally we're kind of trying to prize questions out of people at the end, but I'm going to be driving you for this whole session to give me material to work with.
Well, I went to an outreach event and a couple of the locals brought along their dogs, and that one of them showed me down the mirror, and he said, "Oh, you know, how do I clean the mirror?" And I sort of looked down, and I had a bit of dust on and cobweb and stuff, and I said, "Oh, don't worry about it." Does that sound right?
I'm going to talk about that specifically when we get to cleaning, but it's a really good question, and it's one I get all the time. So being curator, I get people coming to me all the time. I get people bringing me telescopes. The general answer, and I'll talk about it a little bit more later, is you probably don't need to. If you're asking the question, do I need to clean my mirror, the answer is no.
Having said that, that one does actually need cleaning now.
Really? Really?
Yeah, it's had a lot of moisture on the mirror and see around the edges.
Ah, yeah.
It's still okay, but it's getting...
We'll have a look at that when we talk about it.
You're getting a lot of scatter from that part of the mirror now.
So setups. Everybody here is a wizard at setting up telescopes. Nobody's got any questions about how you set them up. That's amazing. We've picked a hugely talented bunch.
Sometimes you get good tracking and other times you don't get good tracking.
Yep. So.
Go to equatorial mount.
So with an equatorial mount, and this is one that's portable that you set up every time you go out.
Yes.
Almost every time it's your polar alignment. So does everybody know what polar alignment is? I mean, I talked a little bit about it as if you did before, but yeah, I saw a lot of people looking at me confused.
See that scope over there is probably a good way to
It is
explain
a good way to explain it. So when we're looking through a telescope like this is an Altaz telescope, and what that means is it moves in altitude, which is up and down. So think of a plane moving up and down in altitude, and in azimuth, which is left and right. So this is pretty easy. So we find a point in the sky we want to look at over at the projector, and we point it there. We make sure that it's kind of roughly in line. Can have a look through the finder scope to make sure it's in there, and then we can look through it dead easy. Now, if we want to take a photo, then that's a bit of a problem because the Earth's moving. Now, I presume most people in here have looked through a telescope. Most people in here have probably looked through a Dobsonian type telescope. And if you look at one of the planets, it doesn't stay still. I mean, it's moving pretty fast. So if you haven't, because there may be some people who haven't looked through a stationary telescope at a planet, if you've got the eyepiece, imagine that's the eyepiece you're looking through. In general, if you're looking at, say, Saturn and it's about this big in the eyepiece, it's going to be moving through the eyepiece about this fast. So that's the Earth moving. So if you're going to take a photo of that, now taking a photo of a planet actually isn't too bad because planets are really bright. So we can use a camera with a fast shutter speed or a video camera to take lots of fast frames, and the movement of the planet doesn't matter too much. But if you want to take photos, even like the ones you see on the wall here, where you've got really long exposures, you might be exposing for 20 seconds or 30 seconds or a minute. The exposures that we do out at Kumio Observatory are 5 minutes each. Then if your telescope isn't moving, then all you're going to see is the stars streaking through the image. So they move really, really quickly. So what you've got to do is you've got to actually have your telescope track it. Now in Altaz, so we're just talking about the AZ Pro, which is a tracking mount. That will track. So the computer knows where the stars are. It knows what time it is. It knows what location you're at. And it knows you set it up to point to a known location. And the telescope will move and follow the stars. Now, actually, big professional telescopes are Altaz, and they do that. But there is a bit of a problem with that if you're going to use it for photography. Now, I do have a slide for this, but it's on a different presentation, so you're going to bear with me, and you're going to imagine this. So if you see the moon rising, and let's say the moon is rising, hang on, moon's rising over there, and it's going that way. So you see the moon rising, and you look at it, and when you look at it at the horizon, you kind of look at it like that. I'm stood here, and I'm looking at the moon, the bottom of the moon's there. Now, when the moon's getting up there, bear in mind the sky is moving. The sky appears to be moving, the floor is moving. When I look at it, the moon's actually rotated, because that bit that was on the bottom when it's down there, where my thumb is now on the side when it's up there. So my telescope there, when it looks at it, is seeing what was the bottom of the moon to be the side of the moon. Does that make sense? That's called field rotation.
Another way to explain it is actually quite good, is the Southern Cross.
Yep.
Because it's circumpolar, so it's just going around and around the South Pole in the sky. And the Alpha Crucis, the brightest star, is always the one further away from the pole. So when it's down the bottom, the Southern Cross is actually completely flopped over.
Yep.
And so if you're following that with an Altaz scope, you'll see the Southern Cross is actually rotating in the field.
But that happens everywhere on the sky, not just at the Southern Cross. So even the moon or the sun or the planets.
There's actually a complicated formula that tells you the rotation rate in different parts of the sky.
So in big observatories where the telescopes are mounted Altaz, and actually you can get them, amateurs can use them. Actually, if anybody saw Simon's presentation, he talked about using one. You can get a rotator, and that will use complicated formula to work out where am I pointing, what is the rotation of that star. So you've got to de-rotate the image. So if you put a camera on an Altaz scope, it won't streak because it will be tracking, but it will streak in a circle, so it'll rotate. So in order to combat that without having to turn the camera around and have a lot of complicated machinery to do that way, is actually to put your scope on a tilt. And that tilt is the axis. If you imagine a line through the north and south pole of the Earth, that tilt is parallel to that line. So as the Earth is rotating, you turn the telescope backwards, so essentially the object is staying still. So that's an equatorial map. But for that to work, you've got to have that line so this, what I'm talking about, this axis here. So this line here. You've got to have that pointing directly at the point on the sky which is above the South Pole, the South Celestial Pole. If it isn't, even fractionally, then you'll get Neville's problem. So that the stars won't track properly. You'll take an image and they'll seem to be moving. You might not be able to point properly, so you move from one part of the sky and then your telescope go-to system says, hey, Saturn's supposed to be there, and you see Saturn, you move to the other side of the sky and you're supposed to be looking at Omega Centauri, but it's not there, it's slightly off. So your polar alignment is almost certainly not accurate. How can we combat that? A few ways. Now, if your telescope is fixed, if it's something like that and it's bolted to the ground, then you can spend a few nights watching if the stars are moving, so as you're tracking. So that one doesn't have a motor on, but if it was tracking, you can spend some time looking at it and pointing two different areas in the sky. If you're interested in learning how to do drift alignment, come see me and I'll point you to some resources. And you can say, are the stars moving? By the direction they're moving, you can tell whether to move it up or down or left or right. So that's looking sort of over the meridian or looking over one of the horizons. So you can do that. It takes time. It's iterative. So you might spend a few nights doing it. We spent at Kumia, we probably spent 3 nights doing that and getting that refined. If you've got a portable mount, then if you're in the northern hemisphere, then it's easy because there's a bright star about a degree from the North Celestial Pole called Polaris. So you can use a very small telescope, which is built into a lot of mounts, to look through there and say, is Polaris where it needs to be, just off to the side? Yes, it is. Then we're lined up. Here, we've just got a big blank piece of sky above where the South Celestial Pole is. So you can't really see the star Sigma Octantis that's there. So there are tools you can buy. You can buy a camera that will do it with a computer that will help you get that lined up. But yeah, that's it. That's a huge setup challenge. And I actually have a whole talk on equatorial mounts, which I might do again at some point, to talk through how you do that and how you do drift alignment. That's cool. Any more setup things?
When you're entering the information into your hand controller, you do your time, your date, your location. Some of them ask for elevation. Why does the mount need to know your elevation, and how important is it to be accurate?
It's not that important as far as I've ever seen. Though if you get to some really high altitudes, I guess that might matter a little bit more because it'll be probably to do with calibrating the GPS signal that it's getting. So that's going to have a factor. There will be some differences because as you get, if you go really high, then your horizon drops correspondingly, and refraction is going to change as well. So I guess it depends on what corrections you've got within your mount for that. So refraction is going to be a lot lower. So I've never noticed any difference. I've never been particularly paranoid about setting elevation correctly. It should pick that from GPS anyway.
Yeah, no, it's
If you've got GPS, you wouldn't have to enter your location and time.
I've noticed that the GPS doesn't pick up your elevation properly anyway. Like on my phone, it can range from about 15, 20 meters elevation difference at different times of day.
Well, your phone's going to not necessarily just use GPS for elevation because your phone has potentially got a pressure sensor built in as well. So that's the thing with using your phone as I've used my phone for all kinds of things in astronomy as maybe an inclinometer to measure angles. So if I'm setting up my mount, or use it to measure north-south, looking at the compass, which is supposed to be corrected. But yeah, if you actually, and I tried this, if you put your phone in one of those plastic boxes that you can suck the air out of. I actually imploded one of these boxes by sucking too much air out. You can actually see the elevation change. So yeah, those boxes you used to get from New World, and with the little pumps, don't just keep pumping because the boxes do actually implode. Speaking from experience.
Well, just one thing, if you are on a site where you always set up in the same place, it's quite useful to know what's called the meridian line. In other words, the line that's true north-south. You can use a compass, but you have to correct for what's called the magnetic declination, and you can actually get maps of that, but they change over time.
Yeah.
Sometimes the compasses in cell phones can be quite good, sometimes they're not so good, and they will normally correct for your local magnetic declination, but they're probably okay for a first cut at knowing where the north-south line is for setting up your telescope. What some people do is, once they've got it right, they mark the tripod, the positions if they're on concrete, so that at least you know you're pretty close when you set up at the same location next time. The proper way to do the north-south line is to, I think you've done this, Steve, out at Q,
Yep.
you use a plumb bob, and you look at dateandtime.com to find out the actual time of local noon at your date and location, and then you look at the plumb bob shadow at that time, mark it, and that's your north-south line.
So when we set up Cumia Observatory, we took the old telescope out and we put a new telescope mount on the pier that was set up there, and it was completely different type of mount. So when we took the old one off, there was a line scribed on the pier, and we made we never assume anything, but we did, made the assumption that must be the north-south line because that's roughly north-south. So we put this new mount on, put it north-south, and then say, yeah, we're great. And we started to do the drifter lining I mentioned earlier, which is looking at stars and are they moving. And we could not, we spent a night on this, and it's like, we just can't get this in. It doesn't feel like it's right. The whole range of movement we've got, it's like, it should be a lot further right, and I don't know why it's not working. So the next day, I went out to the observatory, and we looked at what time solar noon is. I raided my garage and got a plumb line, well, a bit of string and an old fishing weight, and hung that to the dome shutter, lifted the dome shutter up, so I had a piece of string dangling down. Opened the shutter up, and it was raining. So I closed the shutter and sort of sat there. It's going to be another 15 minutes. I looked outside. Still marginal. It stopped raining. Then, luckily, like about 30 seconds before solar noon, we got this gap in the clouds. So opened the shutter, and where the line was, obviously the sun makes a shadow. Now at solar noon, which you just look up on the internet, that shadow is perfectly north-south, completely perfectly. You don't need anything else to check it, you just need your eyes. So I drew a line. And if my mount was mounted like that, the line of true north-south was like that. So yes, that line that was scribed on the mount was completely wrong. So we unbolted it all, drilled new holes, and bolted it back down. But if you're going to do this yourself, particularly if you've got an equatorial mount and you want to line that up so it's north-south, then absolutely, if you've got a place where you observe from on the driveway, do that, make a north-south line. Once you've done that, a lot of people will mark the tripod. The way I like to do it is to spray paint or mark a line on your driveway, which is true north-south. And then I like to get a line 90 degrees to that, and then put that down as well. Spray paint that into your driveway as well, or put some other marking onto your driveway. Then when you put your tripod down, one of your legs on the tripod is kind of a north-south leg, and the other two legs are east-west legs. So if you put your tripod down on this cross with one leg on the north-south line and two legs on the east-west line, then by default your tripod is lined up. So that's probably for Neville, I'd recommend that you do that. I recommend you go out and you get a plumb line at solar noon, look that up on the internet what time it is, draw a line on your driveway where you're setting your telescope up, draw another line 90 degrees to it so you've got a cross, and then plonk your tripod down there and you're going to get a good starting point.
I don't have I can't use the driveway, I can only use the lawn.
So it is and it isn't. I mean, if for a lawn, and a lot of people have this problem. So they're setting up, they've only got a lawn. Either they've got the tripod and it might be sinking a little bit, or it's hard to mark it up. Just get 3 small paving slabs from Bunnings, like the 200 by 200 paving slabs, and plonk them down. Do your shadow line, work out where that is, and then you can even, I mean, when I was doing some work in my lawn over summer, I needed to mark out an area and I spray painted the grass. It's good for a temporary thing. Do the same thing, paint a line 90 degrees, and then put your paving slabs on those 3 arms where your tripod goes, and then leave them there. So yeah, you can. If you've got a lawn, you can mark it out. And you'll find that it's way better because your tripod doesn't sink into the grass. Because that might be one of your other problems, Neville. If you've set up and everything's polar aligned, and then slowly over the night your tripod's digging its way into the ground, you'll find out you don't end up where you start. So let's move on. I think we've sort of done setup death. And we'll talk about collimation. So this is kind of, everybody hates collimation. So this doesn't have an Astron's logo. This isn't a real one. So there are a whole lot of tools, and there's a whole lot of mythology, and there's a whole lot of drama, and there's a whole lot of panic, and there's a whole lot of angst, and I understand it. Because when I got my first telescope, you go on the internet and you type in, you see it in the manual, telescope might need collimating. And then you go on the internet, you type in collimation, and what do? You get horror stories of people saying, I collimated my scope, and I tried to collimate my scope, and now I can't see anything, and I've broken it. I can't make it work ever again. You hear about, these telescopes come from the factory. These mirrors are perfectly aligned. So in reflector telescopes particularly, you've got two mirrors. You've got a mirror at the back, and you've got a mirror at the front, and the light comes in, and it hits the mirror at the back, and it bounces off that mirror, and it hits this mirror, and it comes out the side for a Newtonian. It comes out here. Now, if those mirrors don't line up perfectly, you're not going to get a good image. So it's really stressful. As a new telescope owner, you think, okay, well, we've got these adjustments. There's adjustment screws here. Bill's going to hate me in a second. And there's these lock screws. And what if I was to accidentally move one of these? Well, now my telescope is completely not collimated, and I've just stuffed up the collimation on Bill's telescope. And if that happened to me when I first got my first telescope, I'd have probably, my heart would sink, and then I'd probably beat me up, and then I'd be like, oh my God, I'm never going to get that fixed. It's too scary.
Save the cat, doesn't it?
Maybe. Well, it'd be better if I had a SCT. That would work more. Sorry, astronomy joke. So what is it? What is collimation? It is simply the act of making the mirrors or optics in your telescope, because you can collimate a refractor, aligned to the path that you're looking, so an optical axis. So the mirrors have got a tilt on them. So these screws on here, these black knobs are attached to they're attached to the mirror, and it moves it. So as I'm screwing this in and out, the mirror is tilting slightly. So you see there's knobs on the back there. You can come up afterwards and I'll show you. We'll do a demo of collimating using a laser. These white ones just lock it in place. So they're just a screw that pushes against it and it locks it in place. It's not difficult. On a Newtonian particularly, it's not difficult. Once you understand how it works and you become not scared of it, actually you realize with a Newtonian, and Niven will have to do this quite regularly as you're moving it around, they do move out of collimation because these mirrors are quite heavy. It's not just a little bathroom mirror in here, it's a big thick chunk of glass. So it's quite heavy. And so as you throw it in the car, even though it's tightened up on these screws, it'll slip slightly. So it won't be quite collimated. So learning how to collimate and owning, so if you've got a Newtonian, then you should have a laser collimator. So it's I can use it as a pointer, that's cool. So this is a laser collimator, that's this one. You should get one with an Astron's logo, not a GSL logo. This is another laser collimator, it's called a Howie Glatter. He used to make really, really accurate laser collimators. Unfortunately, he passed away a few years ago. This is a way of doing it without a laser. This is a sight tube, which is basically just a hole, so you can look through and you'll see both the mirrors. This is a Cheshire, which is a sight tube on steroids because it's got two pieces of wire on it. And then this is a really expensive Takahashi collimation telescope. I've got one of those in the box down there. That's for collimating Cassegrain telescopes and Ritchie-Creation telescopes, which actually are a little bit more finicky to collimate. With a Newtonian, it's pretty easy. You put one of these in the eyepiece holder. I'll demonstrate it shortly. You come around and I'll show you later rather than me trying to demo it to you all while you sat down. You've got a laser. You put that in the eyepiece. You point the laser into the telescope. That laser will reflect off the secondary mirror and you'll see it on the primary mirror at the bottom. You make adjustments so that it's pointing directly so that the laser beam goes directly at the center of the mirror, which is marked with a circle. And then you adjust the bottom mirror to make sure that that beam points back up and goes straight back into the hole that it came in. It's that easy. I'll demo it for you after the session if you those are interested.
If you've got a telescope with a mirror that isn't centre spotted, then the first thing to do is to actually see the spot in the mirror.
So yes, so some smaller telescopes don't have a spot in the mirror. So if you come up and have a look here, you'll see that the mirror has got a dot in the middle of it. Some telescopes come without that, particularly smaller ones, and they're really hard to collimate if they don't have a dot in the middle of them.
Like my 4.5.
Like your 4.5 inch one. Now the best thing to do with that is to put a spot in the middle. How do you do that? Well, you can get a ruler and measure the mirror, the middle of the mirror, put a dot in it. What I tend to do with the smaller ones is I print out a circle on a piece of transparency on my laser printer with a X in the middle, and then make a little small hole there, and then just dot it with a permanent marker. So line that up. So definitely you should do that. When you get into Ritchie-Creation telescopes, ICTs actually, so Schmidt-Cassegrain telescopes are actually really easy to collimate. They've only got 3 screws on them. On the secondary, you can only adjust the secondary because the primary is spherical, so it wouldn't make actually any difference if you tilted it. It would still be a spherical surface if you tilted it one way or the other. But you can really only collimate them on a star. So there are tools, but there are not very many tools to do that kind of during the day. So with that, you defocus the image. Now, when you look at this, I mean, anybody, give me some questions about collimation, actually. Give me some guidance on what you want to know about it and what you don't know.
Well, Gareth's not here, so I'll embarrass him. I was just going to show you this. The laser, you notice, has got a 1 1/4 inch barrel, and most of these GSO or Astrons Dobsonians have a 2-inch focuser. So of course you have to use an adapter, and you'll see that it comes with a 2-inch to 1 1/4 inch adapter, and you can plug the laser in there and it's all fine. But what he was doing is, this is a Barlow lens and it also comes with one of these adapters. Problem is that you notice the screw positions. That one is on the ledge. With the Barlow one, it's actually into the barrel. And then unfortunately he was using one of these. And the problem is that it never sits square, and he couldn't work out why with the laser he could not get his telescope collimated. It was just because he was using the wrong kind of adapter. So that's just a little trap. Be careful that you have one where the rim of the adapter actually is firmly square with the focuser. Otherwise, the laser is just going to flop around. So that's a little trap. I thought I'd mention.
Definitely. Go on.
All right. With my Dobsonian, it's just got screws at the bottom end.
Yep.
Is there an easy way to identify which are the lock ones and which are the actual?
Yeah, absolutely. So usually the lock screws, or true in all cases, the lock screws are really just push screws. So they're not attached into anything. So they're just pushing against the mirror cell. So if you look on here, they're not screwed into anything. All it is, the mirror cell is, just put that down. So you imagine the back of the mirror cell. The adjust screws, or the pull screws, are the ones that are threaded into the mirror cell. So when you tighten them, it will move the mirror cell backwards and forwards. The lock screws actually just push on that mirror cell to hold it in place.
My Ukrainian 6-inch has got doesn't have the black and white like the Dobsonian.
No.
But it has the large silver one and a small one.
Yeah, usually they're different. So there's usually a big screw and a little screw, or a black knob and a white knob, or a big black knob and a little black knob. Usually there's some difference, but the way to tell is that and some telescopes, they don't call them lock screws and collimation screws, they just call them push and pull screws. So one is pushing against it and the other one is pulling against it because it goes through a thread. So you're tightening it up. So the lock screw doesn't go into the mirror cell. That's how you remember it.
There's another secret there I recognise it as, I can't remember, is the adjustment screws have springs on them with lots of
Yeah. So on the GSO ones, that's certainly true, but it's not generally true. It's true a lot of the time, but it's not necessarily true.
What's the easiest way to tell if your telescope requires collimation?
So the easiest way to tell is that your stars, particularly on axis, so in the middle of your view, are not round when you are at or very close to focus. So you'll get, so you'll be familiar, you may or may not be familiar. When you look through a Newtonian telescope, particularly around the edges, often the stars have got little tails on. We call it coma. If you're starting to see that coma on axis, so in the middle of your view, you know that your collimation isn't right. You know that there's something wrong. Now, oftentimes with collimation, you'll see it shown in books and guides about how to do this or how to check on a star, how to do a star collimation, and they'll show you a nice little diagram showing that if you just take it out of focus a little bit, what it's supposed to look like, and it will often look like this. This is another one of those things that confused me a little bit when I started looking, because you get these nice perfect circles that have been rendered from a computer, and often it doesn't look anything like that. If you're looking at the real sky, you don't really see anything. But imagine that's slightly out of this is slightly out of focus. But imagine if you were more in focus, you'd have a star and it would have a bit of a tail going off to the right there. So when you start to look at your images, they'll sort of have little tails, and that's how you tell that your collimation isn't right. And if you take that just slightly out of focus, and the other thing is so the circle there is the shadow of the secondary. But oftentimes when people look at this and they say, hey, collimation, you take it out of focus and you look, people take it way out of focus, and you can see this big donut, and you can see the spider, and you can see everything like a projection of the front of your telescope. That's way too out of focus to check whether your collimation's right or not. If your collimation looks out and you can clearly see the spider and everything, then yeah, it's going to be completely terrible. You actually want it to be just out of focus. In fact, if you're going to do star checks with collimation, and I've got a really good guide on how to do a star check, so if anybody's interested, come and ask me afterwards, you want to be just out of focus. In reality, what it looks like when you're just out of focus is more like this. So that's kind of a bit more of a realistic look of what you're going to see. So you don't see those beautiful nested rings that come all the way out that you see in the computer renderings. So the one on the left, just out of focus, that's out of collimation. So that's what you'll see on a telescope that isn't collimated very well. The one on the right, that is in collimation. Now, sometimes these rings aren't very well defined, particularly if the seeing isn't very good. The way that I kind of think about it is, rather than, is there a bigger gap here than there is here, is there a really bright bit on one side? Because that's actually easier to see. You can see that this is brighter here than it is over there. And that's kind of one way to look at it. When your telescope is quite close to collimation and you've got a view like that, and you can actually see it in here, but it's not that. You actually see it on both. You see a little dot in the middle as well. And that's called a Poisson spot. And that's as a result of the central obstruction, the mirror, and the diffraction around that central obstruction. The light actually makes it past that and goes to a point in the middle. Now, as you get further out of collimation, you can see it here. Can you make out that little dot? Come up and have a look later if you can't quite see it. That isn't quite as well centered on that image as it is on that one. So as you get close to collimation, that Poisson spot, if you can see it, and your seeing's got to be reasonably good, will help you just make final adjustments. Because all of these tools like the lasers and all the fancy tools you can get, the $600 Takahashi collimation scope and the Howie glider laser and all of those only get you so far. You got to take your telescope out and put it under the stars and have a look. So you can spend all day collimating something, it looks like it's perfect. Ask me, I've done it. Ask me how many hours I've spent at Kumiu trying to do this. And then you point it at the stars and it's just rubbish. It's just nowhere near. So you've always got to do that final tweak on the stars. Anybody got any horror stories on collimation? Or?
Yeah, pretty much have a look at the lasers. You can get two different types, and if you get the wrong type, it's a pain in the butt. My one I got is quite good because it's got your 1 1/4, but then it's also got the 2-inch adapter on it. The only thing that I really hate about it is that it doesn't have the 45-degree angle on the target, so it's just flat.
This here,
Yeah.
basically a partly transparent screen here, so you can actually see the return when you got this in the eyepiece holder, you can actually see the returning laser beam, whether it's centered or not.
So the trouble with it is that if you've got a friend with you, it's really good because they can stand all the way up at the eyepiece. I've got a 12-inch stop, so it's quite far away from me. And you have a lot of fight going, oh, turn to the left, oh,
Yeah.
which left or which right. But if you have the one with the 45-degree angle on it, you can actually angle it, and it makes it a lot easier for you to have a look from the back as you try and tune it by yourself.
Yeah, so this is quite expensive and very rare now because the guy who made it died. This is one of the Howie Glader lasers. And they're made super accurately, but they don't have the 45 degrees. So if you use this, you see you've got a screen on the end of it. If you were to use this to collimate, actually you've got to be able to see that screen inside the eyepiece. So if you were to put that in here, you'd have to be able to see that to see whether the light was going back in, so it doesn't have the 45 degree.
Mine's got the cutout, but you've still got to look.
Oh, you got to look underneath. Yeah.
The Howie Glader one used to have an accessory which was built in Barlow lens and a bigger screen.
Yeah, you can get one of those.
Basically, what the idea is, the Barlow lens, instead of having a laser beam being a thin pencil, as you know, like that, there it is. The Barlow actually causes the beam to flare out. So when it hits the main mirror, instead of being a point, it's actually a big disc. And what you do is, there'll be a centre dot or a centre circle. This one's actually got a circle, like a ring binder thing with a hole in the middle, so there's a reflected piece in the middle. What happens is the reflection of that comes back to the screen, and you can actually see a dark ring that represents your centre dotting circle. And so you actually, if you can see that, you actually use that and centre it on the hole that the laser's coming out of. And that works for really fast mirrors. It's quite an accurate way of collimating the primary. Have a look up on the internet, it's called Barlow laser collimation.
Yep, a couple of questions out from the internet actually. One I'll deal with now and the other one I'll deal with in a minute. I've got a question which is, I've got a 10-inch dob. Does anybody have any ideas how to firm up the spin left, right on the mount? So the answer to that is, on the Astron's dobs, there is a knob on the base which you can tighten up. So that will increase the pressure on the bearing plate there. Sometimes that's a little tricky. So and sometimes those, if they're older ones, sometimes they kind of pull loose a little bit. So disassemble the base and just check everything's in place. But you tighten up the knob on the bottom, and so there's a little hand wheel on the bottom, and obviously for your altitude, tighten up those ones.
Also, speaking on that, make sure the washers, the roller bit washer set that's in there is in the right order.
Is in the right order, yes. So as we know from experience, it is possible to put these bases together incorrectly, and they don't tighten up. So there is a guide on the Astron's website. We've got a video on the Astron's YouTube channel, which tells you how to assemble the Astron's Dobsonian bases, and pay particular attention to those washers.
On the Sculpture ones, you can do the same thing, but it's use the two spanners through the package.
Yep, to tighten it up. Yep.
The same idea.
So yeah, it is just tighten those screws. Is there anything else on that, or we'll move on to, I know we're getting on for time now, so move on to a little bit of a question about cleaning.
One more thing.
Yes.
My 6-inch is a little bit out of collimation. It does show 2 comet tails.
Yep, that's all you'll see if it's out of collimation.
I've got an 8-inch case screen. I probably don't need to collimate it yet because it's still pretty new. But I went on it's one of the Astron's ones, and I went on Andrew recommended to go online to search up the manual. They say in the manual that it's meant to come with a little kind of thing that goes in the eyepiece with a dot on it. But
we're going to get supplied with that.
Yeah.
But for the classic Casas or Casagrains, I have found that a star collimation works the best. Come and see me after. I'll give you a link to a post that's on Cloudy Nights, which gives you a really good procedure for doing a star collimation. I'll probably put it up on the description for the YouTube for tonight and put it on the website. I think it's a fantastic guide. It really describes how I would do a visual collimation. The pictures are a little bit computer generated, so you've got to kind of interpret what that means when you're looking through the eyepiece. I would normally use a camera. I use an SLR on the back and just keep taking photos. I'll use the live view to do the collimation and see the change in the patterns. But it's all about defocusing it slightly. But it's a good procedure that gets you, it tells you how to do the primary and secondary mirrors, which is actually a bit of black art if you don't have somebody explain it to you. So I'll give you a link that will give you a really good process that I've used myself on the classic Casas. Because they can be a bit of a challenge to use any of the tools with, just because of the setup and because of the baffles. The baffles make it tricky.
While you're on collimation and lasers, do you want to just quickly go over how the laser itself may also need collimation?
How the laser itself was?
Well, I can need
collimation. Yeah,
the way you can do that, I don't know how well this one is. Put it on here, and you, I'm not doing it flat, but basically when you roll it, the dot shouldn't change height.
What we will get is, there we go. So your laser itself might not be collimated. So in order to check that your telescope's collimated, this laser beam here, must be coming out perfectly down the middle of this tube. So the way to check that is to get yourself some V-shaped blocks and hold your collimator on a V-shaped block. I'm going to do it in my hand, so it's not really optimal. And then turn it around while you're watching it on a wall a long way away. So the furthest wall you've got. And then what I would normally do is I'll stick a post-it note on the wall with a cross on it, and then turn the collimator around while you've got it on some V-shaped blocks. Just cut some notches and some pieces of wood. It's simple to do.
That's much more accurate than my scheme of rolling it along a bench.
Yeah, rolling it on a bench isn't all that great. With these, because they've got this hump on it, it's actually a little bit tricky. So you get two V-shaped blocks, and then just move it around. And if I was holding it straight, I could put it on the table here.
See if this one needs any tweaking.
So we can see, I'm not holding it very still, but... So as I'm moving it around, you can see that it's
out a little bit, isn't it?
It's out a tiny bit. It's not too bad, but it is moving. It's scribing a circle. Can you see that? So what that means is that when Bill fixes his telescope that I put completely out of collimation before, it's still going to be out of collimation. So Bill's going to really hate me.
Well, with an F6 mirror, it's reasonably forgiving.
It's not too bad. We had a look. If we could have a look at this one. This one should be reasonably well collimated, although it has been in a.
So what do you do if the laser's out of collimation?
So on the lasers, I'm not holding this very straight, but so on all of the lasers, pretty well all the lasers that we sell or the lasers that you get, you see that there's little holes all the way around at 120 degrees. So on here as well, there's a grub screw. So you can that all is in there is the laser is in a little tube, and these grub screws are holding onto the tube. So a little bit like collimated telescope, you tighten one, you've got to loosen the other two. So you do it until you're putting it on your V-blocks. And I've found clamping the V-blocks to a table is, it's just hand holding it isn't really good.
It's like lighting up a kaleidoscope.
Well, yeah, it's sort of like that, yeah. But the more accurate you get that, the easier it is to get your telescope accurate.
One thing I noticed with collimation, and I fell into this trap, is going too far initially until the screw comes out.
Oh yeah, you can do that. A really good tip with collimation to avoid that is, because your telescope's probably not too far out of collimation when you start, is actually to only adjust 2 screws. So never touch one of them. There's 3 sets of collimation screws. Mark one of them and never touch it, because you can get all the range of adjustment you need with just 2 of them. So, because if you keep adjusting it, you adjust all the screws. Remember, so the way that these screws work is the mirror is held on a plate, and some of these screws are threaded through it, and they're holding the mirror up. If you keep unscrewing them, so if you only collimate by unscrewing, which is going to move the mirror tilt, eventually the mirror is going to fall off the end, or your screw's going to come out, which is the problem that Robert's had. But if you only ever adjust 2, you've got essentially a fixed point, and you're adjusting against that fixed point. Now, if you've got a Ritchie-Creation telescope, it's super important that you don't adjust all 3 screws, because the spacing between the mirrors is critical. So if you adjust the spacing between the mirrors, you're actually going to affect the configuration of the mirrors. So you're going to have other problems other than collimation. So
supposedly you can set mirror distance using a Ronchi screen. I don't know how easy it is.
You can do that. I've never had actual real luck doing it, but I do have a Ronchi eyepiece here. So if anybody does ever want to try that, I have one. Final topic, I know we are getting a little bit late, is cleaning. So people ask me about this all the time. So my telescope is a little bit dirty. When should I clean it? Well, my eyepieces are dirty. Now you left, but this is a real, actual cleaning. So, so this is actually this is a test mirror for the James Webb Telescope, and that's being cleaned by carbon dioxide snow. So that's actually really cool. So if you're a pro, that's what you do, and the way that works is you use the carbon dioxide because I guess it's hard, but it's not as tough as the coatings. You can dislodge any grime, and then it sublimates, so it doesn't leave anything on the surface. So this being one of the biggest challenges with cleaning optics is you have this uncontaminated surface, and if you do any cleaning, you're risking contaminating it or worse, damaging it. So Bill says his telescope needs cleaning. It's probably just about getting there. If you have a look at Bill's mirror, it's got a lot of marks, a lot of watermarks around the outside. But in general, if you need to ask the question, should I clean my telescope mirror? The answer to that question is a resounding no. If you've got a spot of dirt on there or a dead spider or something like that, and you think, my God, my telescope's going to be terrible because of that mark on there, just remember how much of a space is covered up by your mirror, and that doesn't affect your view. When you've got a Schmidt-Cassegrain scope, you've got a giant hole in the middle of your mirror this big, and it doesn't affect your view. So a bit of dust on your telescope mirror is really not going to affect your view. What will affect your view is if you take that out and you scratch it and damage the coating. So there's a few things that people will need to clean. So eyepieces, definitely you need to clean. The other question I had from the internet is, which is a good one, which is, how do you remove mold off the primary and secondary without destroying coatings on a Schmidt-Cassegrain? So Schmidt-Cassegrain has got a glass corrector plate on the front, and sometimes if they've been in humid conditions like camera lenses, they'll get mold on the inside of that.
I've often had a question, people have had installed it like in a outhouse or a barn like that, real property, and they're picking up 10 years later and think, we should use the telescope, but it's
Yeah.
old.
So the answer to how do I clean it is either not at all or very, very carefully. So with eyepieces, now eyepieces, the biggest thing with eyepieces is you're putting your eyes next to it and your eyelashes have got oil on them. And so eyepieces are going to get dirty. There's no question about it. It doesn't matter how careful you are. Even if you spend $1,000 on your eyepiece, as soon as you start looking through it, your eyelashes are going to deposit oil on there, and that's going to pick up dust. So they are going to get dirty. So eyepieces that do have coatings on them. So the thing you're worried about with optics is the coating. So they put, the same as those of you who wear glasses, you'll know if you go and you can ask to have coatings put on your lenses, it costs an extra couple $100. And what it does is it means they reduce reflections, they make more of the light come through rather than reflect off. But on a telescope, these coatings are really important because you want to get as much light as possible. But on a telescope, these coatings are really, really fragile. Now, if you wear coatings on your glasses like I do, you've got to be careful with them. But on a telescope, you've got to be really careful. Now, an eyepiece is not too bad. The coatings on there are probably more similar to the coatings you might find on your glasses, so they can cope with a bit of cleaning. They're designed, they're expected to cope with a bit of cleaning, but you should be really, really careful. The biggest killer for it is grit and dirt. So if you need to clean it and you've got any dust or anything like that and you wipe it, then you're just going to scratch that coating. Now, once you scratch the coating, then that's going to reduce your view because that scratch is going to diffract light. So it's actually going to make your eyepiece have less contrast. So you're going to be really careful. How do you clean it? So I make my own solution. This solution was given to me by the previous curator of instruments. So it's super secret. It's not secret at all. So how do I do it? I have 2 bottles. This is kind of my go-to cleaning thing. And tissues. Right. Now tissues, plain white tissues, no aloe vera in them or anything like that, are just fine. Kleenex ones are actually the best. don't get recycled ones. They've got all sorts of crap that have been recycled in them. So just plain white tissues are good. I will sometimes use like sort of medical gauze as well, but not for anything really sensitive. But that's quite good because it's sealed and you know there's no dust and dirt in there. Now this is my super duper mix. What is in the mix? Demineralized water. That's super important. So you get go to the car dealers, go to like Repco or Supercheap, buy demineralized water. It's used for batteries and irons. People used to put that in irons so that they don't fur up. But demineralized, not deionized, but demineralized, so there's no minerals in it. Reason being, when normal water, tap water, evaporates, it leaves behind like the calcium carbonate and other minerals that are dissolved in it. And that's what's going to give you water spots. And when those minerals go hard, they're really hard to get off. They are rock. So demineralized water, and then isopropyl alcohol, which you can get from Bunnings, Mitre 10, whatever. So I use 30% isopropyl. Most of the rest of it is demineralized water. And then a few drops, like not a huge amount, literally a few drops of normal dishwashing liquid. So each of these do a different thing. So the alcohol acts like a solvent. The dishwashing soap allows you to remove oils. And the water obviously just holds it all together. And then I have a bottle of just water. So this is just demineralized water. Now the way that you would clean an eyepiece, with that, I don't actually have an eyepiece, which I should have really thought about that.
Oh, hang on, I've got some here.
Oh, Bill's going to make me clean his eyepiece now.
Well, no, I'll give you the society one.
Oh, the expensive one. You want me to do the expensive one? Oh, thanks for that. In a live studio audience.
No pressure.
No pressure. Just destroy the expensive eyepiece. This actually isn't.
The one that I introduced.
It may not be too
It's
bad.
not
It hasn't
too
been
bad.
used a lot.
It's not, but not too bad.
This is for the Zeiss, this one, and it costs more than one of those telescopes.
So the first thing is, don't spray the liquid onto the eyepiece. Just don't. What I normally do is I'll mist it. So this is, I probably would start with water, but it doesn't really matter. So I've just made that a little bit moist. And the first step is just dab on there. And then don't reuse the same piece of tissue ever again. Actually, even the bit you've held, you probably shouldn't do. And you're just dabbing it on. And what that's doing is that's removing any dust that you've got accumulated. Now I've dabbed that, throw it away. Tissues are cheap. You don't need to reuse them. So keep doing that. And then once you've done it quite a while, once you've done it for a little while, you'll notice that as you're putting it on, you'll feel that it gets smoother because any dust is kind of you're picking up. Try not to drop the expensive eyepiece. It's even better actually, I mean it's not too bad with an eyepiece, but if you're doing it with anything really sensitive, I'd probably wear gloves as well. So you're just not getting you're not accidentally getting the oils from your fingers on there. So slightly moist, dab it on, and keep changing the tissue the whole time. So how do you clean your SCT? You do exactly the same thing. So this is how I would clean it. And can you clean mirrors this way? Sorta. So mirrors are really, really fragile. So mirrors, typically they've got a coating of aluminium and it is, a few molecules thick. It's a really, really thin coating of aluminium. Most mirrors on commercial scopes, though, have a silicon dioxide overcoat, so they're actually a little bit tougher. If you want to clean a mirror, really the best thing to do is just wash it. Just put it take it out, put it under a tap, rinse it off with demineralized water after you've done that, immediately after you've done that, before it gets dry, and just rinse the dust off and then leave it.
Can you use your magic solution on it?
You can use the magic solution, but I would not be rubbing it. You can possibly dab it lightly. I did Gareth's one this way because that had got insects in it. There was all kinds of gunk all over it. That was really bad. But you've got to be super careful. It's really easy to damage a mirror. General advice is don't.
After this was with my 4.5, I did wash it from time to time because it's got salt on it.
Yeah.
Crystals of salt.
Yeah, salt actually is a problem. So if you're in a coastal area, you can get a bit of sea spray in the air, and salt does crystallise on there. So yeah, use your judgment. Use your judgment.
And what I did was actually just use the tissue and lay it on the top of the mirror.
Yep.
And just and not move it at all.
Yeah, that is one way of doing it. So yeah, that's actually true. You could lay it on there, not touch it. Use just the weight of the tissue, really. Once you've got the dust off this, you can sort of do some light movements. But yeah, just be really careful. The dabbing movements are actually better.
Dust can often be really hard particles, like very fine dust, which is actually rock. And if you move that around on the surface, it will scratch.
So this is like last resort, obviously, it's cleaning the equipment.
Yeah.
What about storage and other ways to avoid getting the dirt?
Good question. So with Dobsonian, if you've got the room for it, store it about like that. So any dust is not going to collect on the mirror.
Steve's work.
Slightly down, you know, so anything's not going to fall. With some telescopes, you don't want to store them pointing down, but keep them horizontal. Eyepieces, always put the covers back on. Telescopes, always put the dust covers back in the dust cams. Question about moisture that we had right at the start. If your telescope gets full of dew, that's fine on the outside. When you bring it inside, just don't put it straight in the box and close it up, because that's where you start to get mold. So the outside you can towel dry. If you've got an SCT and it's got moisture on the corrector, don't get out your tea towel and start wiping it, like some people did in an establishment not far from here.
We won't mention it.
We won't mention it yet. Just let it air dry. You could use a hair dryer. That would be okay. Being careful though, because you might be throwing dust and bits of hair and things at it. But yeah, if your equipment's wet and you put it away, just leave the box open. Put it in a corner, leave the box open, let it air out. Don't put the covers on fully. Let it dry for a couple of hours.
That one around the edge of the mirror has had that from being out in really dewy conditions where moisture has actually gone onto the main mirror, and probably it's dried on there with some, probably a bit of salt spray.
Yeah, it does look a little bit like salt deposits. So yeah, probably you might need to get at that a little bit. I don't think they'll just wash off.
So you've got your two bottles. Which order do you use them in? Do you use the isopropyl alcohol first and then?
Generally, I'll use the water first just to get anything loose off there. Then the solvent one is what's going to help get your fingerprints or any kind of stuck remains on there. Then finish off with the water, just because there's no detergent in there. You can use, some people will use just alcohol straight. It's sort of okay to do that. I'll clean my glasses like that some way, but it's a little bit harsh. So some coatings will be dissolved in isopropyl. You might need to soak them in it for hours before it'll start to attack them. But yeah, just be careful. That's why 30% is probably about enough to do that. So yeah, water first, just to give it a clean up. Then you can use the solvent just as far as yet. What you'll see with the solvent helps it evaporate quicker as well. So as you'll dab it on, you'll see that it evaporates on.
I find it hard to get it perfectly clean. It always looks like sort of smears.
Yeah, so once you've got the grit and dust off, you can move it around a little bit to get that. But those smears are often caused by impurities in whatever you're cleaning it with. So if you're using water, this is why I use demineralized water. You can, one of the tricks that I've done before is you can use coffee filters to filter like your alcohol, because your alcohol is made for industrial purposes generally. It's not made for cleaning optics. So stack a couple of coffee filters up and filter your alcohol through it, just in case you've got any grit in there. Even your water, you can do that, or your bottle of solution. Make sure you wash out your bottles before you put them any spray in there. So just bear in mind that any of that's kind of can affect it. Other things you can buy lens papers. So they work fine on like eyepiece and things like that. So they're designed to be not as harsh. You can use Kim wipes, which are a sort of scientific grade tissue effectively. That's used quite commonly. The problem with normal tissues is while they're cheap and available, and I do use them quite a lot, is they do leave fluff. So the other completely you've got to have is a bulb blower. So, you know, one of the little camera bulb blowers to blow dust off. Don't be tempted to buy these cans of air, these cans of compressed air. They're terrible because they don't contain air, they contain butane. And if you hold them at the wrong angle, this butane squirts out all over everything. Not good, not particularly pure. It's going to potentially squirt liquid solvent all over your optics, and it's potentially going to get inside it. So don't use cans of air. A bulb blower is the only thing I'll use to get fluff off. Cool.
Same is okay for the refractor front lens?
So the front lens of refractor, same thing. SCT corrector plate, all the same thing. Just being really careful, being aware that if you've got any dust on there and you slide it, that's what's doing you damage. So even if you've got the softest cloth, the softest tissue, the softest Kim White, the softest lens paper in the world, if you've got grit on there and you slide it across it, that's damaging your coating.
Usually refractor designers try to make the tougher, or the outer element tougher because they know people will clean it, like they won't put a calcium fluoride lens as the front lens.
But don't bet on it. Don't bet on the fact that it's...
I'll let you do the solid telescope.
Cool.
Same solution for fungus.
Same solution for fungus. Be really gentle with it. It can stick quite a lot, but oftentimes it's quite easy to remove. Oftentimes it's quite sort of powdery, and you can get rid of it. So if you've got fungus on your lens, same thing. Just be careful. Don't wipe it. Try and dab it off. Don't be afraid of using tissues. You know, you come in my little office if I've been cleaning eyepieces or something. There's tissues everywhere. There's just piles of tissues everywhere, and they just all go in the bin. Way better than reusing. You know, taking grit off one part and putting grit back on somewhere else. Just remove it. A lot of the guides will actually tell you don't even use the bit you've held, which is why I'll normally wear gloves. Cool. All right, well, sorry we've gone quite a bit over time, but that's because of all your great questions rather than me rabbiting on. Well, you're probably bored of me now anyway. So thanks very much. If you want to come and see any of that, come see me afterwards. Other than that, thank you.
Andrew's got the Zeiss telescope operating if you want to have time to have a look, and he's got an extensive lens in it.